Hey everybody, Mr. Mark with you, and let's do a quick projectile motion warm-up together. In this example, we have a motorcycle stunt person right here, and they're driving a motorcycle off the roof of a 12-meter tall building. Do not try this at home. The motorcycle lands on the ground 24 meters away right here, and then we have this random point A that we're going to do a few things with later. But we know that this point is 16 meters this way horizontally from the building. So the first thing we're going to do is we're just going to draw and label the forces on the motorcycle when it is at point A. And so kind of the big idea here is that for anything that can be considered a projectile, what that word means is that gravity is the only force acting on it. And so the only thing I would draw here would be the gravitational force, which as always goes down. So those are the forces on a projectile, anytime, every time. The second thing we're going to do is we're going to figure out how fast this motorcycle is going when it leaves the roof. So now we have like a kinematic situation in two directions. And so it may or may not be helpful for you to kind of break out a table of information into y and x values. Not necessary, especially once you get kind of proficient at this, but if you're having trouble figuring out where to start, this might help you out. So let's kind of do that together for this one. In the y direction, I would go ahead and make the initial vertical position 0, and then the final position, so down here, 12 meters. And what that does is it makes down the plus y direction for me, which is the same direction as the net force on the motorcycle. So I don't have to worry about negative signs if I do it that way. So you don't have to make down positive, but I recommend it. So in my table over here, I'd write y naught equals 0, and then the final y equals 12. Of course, since this thing is free falling, the only force acting on it is gravity, our acceleration is equal to g, and we're going to round that off to 10 meters per second squared. And then because our motorcycle is going horizontally, then the vertical velocity is 0. It's not going up or down when it leaves the roof. Now that vertical velocity doesn't stay 0, but the moment it leaves the roof, the vertical velocity is 0. And then kind of the key to remember is that time is the thing that connects our two axes of motion together. The initial velocity is in the x direction. Since this arrow points in the plus x direction, the x is our question mark, since this initial velocity is our question mark. That's what we're trying to figure out here. The horizontal distance it lands, I can call that delta x. So x equals 24 meters. And if I had the time, then this would be really easy, because in the horizontal direction, the velocity is constant. And so we just go back to our very first physics equation, the definition of velocity, displacement over time. So I have to figure out the time using the vertical axis in this case, and then I can plug it in over here once I've got that. So I'm going to go ahead and set this up. Vx equals 24 meters. And then let's work over to the side and figure out this time. In the y direction, the kinematic equation that's generally going to be most helpful will be this one, the one with the at squared at the end of it. Since I typically know this velocity and I know my acceleration, and time is the thing that links the two together. So it kind of makes it a bit easier, since I always seem to have about the same starting point when I'm trying to figure out what a projectile is doing. This is 0, this term is 0, so I'm going to drop them out. So y equals 1/2. I'm going to go ahead and replace the a with a g, t squared, and then this is something I can solve for t. So multiply both sides by 2, divide by g, take the square root. There is our time. And so I'm going to go ahead and plug in the numbers here. 2 times 12 meters is y, 10 meters per second squared. And then go ahead and crunch the numbers on that, and you get 1.5 stuff. And kind of a really important pro tip is don't round off all that stuff too soon. And so I'm going to leave a few extra digits past that 1.5. Because when I put that number in over here, last step here, 1.549 seconds, if you round that number off to 1.5, and I use the value 1.549, we're going to get pretty different answers for our velocity. And so don't round off this intermediate number. Like, you can round your final answer off something reasonable, but don't round that number off too much. So when you do that division, you get like 15.5 and then meters divided by seconds. So there is our V naught. The second part of this question is like, hey, how high is this motorcycle when it is over here at point A? So I can kind of do the same sort of thing where I have a table and then just kind of adjust the values. So my initial position of the vertical direction is not going to change. However, we're at a different point along the arc, so the final position is going to be different. Same forces, so same acceleration, 10 meters per second squared. It's still leaving the roof the same way, so the initial velocity is still going to be 0. But my time is not going to be 1.549 seconds anymore. We're talking about this point along this arc, not this point. And so we're going to get a number less than 1.549 seconds when we find the new time. So t equals blank again. In the x direction, this velocity is still useful because the motorcycle still leaves the roof at that speed. But now I have a new delta x. So if I go back up here, look at our picture real quick, we're told that point A is 16 meters horizontally from the building. So like this distance here is 16 meters. So I'm going to use that for my delta x instead of 24. So delta x, 16 meters to point A. So we're going to kind of run this in reverse. Time is, again, the key thing here. Since I have these two numbers, I can take our constant velocity equation and solve it for t real quick. So multiply both sides by t, divide by the velocity would give me this. And just plug in our same velocity from before and our new displacement. So 16 meters. That's how far I want to go forwards, over 15.5 meters per second. And again, when you pull the calculator handle, don't round it off too much. It gives me a delta t of 1.032 seconds, which is reasonable. It should be less than the time needed to go all the way to the ground. So now that I've got that time, I can just kind of come back up to this same expression here and get my new value of y. And so if we did that, that would look like y equals 1/2, g is still 10. Now my time is 1.032 seconds. And then we got to square it. So we get a y value of 5.3 meters, 5.3. Okay, now that's not my answer though. This number right here is how far my motorcycle fell. So that's this distance from here to here. This is y equals 5.3 meters. So the question asked me for the height, which I would measure from the ground. So this distance here is what I'm being asked to find. So I can kind of switch around my coordinate systems and make y the answer, but what I find easier to do is just figure out how far it falls and then figure out where the ground is and then just subtract. So the ground is 12 meters away from 0. So the height of this motorcycle would be 12 meters minus that 5.3 meters. And so when you subtract those, you get a height of 6.7 meters. There's our height right there. So there's a big difference between how far it fell and how high it is above the ground. So we just want to make sure we take that into account. You can do that a couple different ways. I think the easiest thing to do is just figure out where the ground is and then do some subtraction to get that height. Last part to this question is just sketch some graphs of velocity versus time for both of these things. Here it kind of gives us the coordinate system. We want up to be the positive y direction. So if my motorcycle starts with a vertical velocity of 0, it's going to speed up, but it speeds up going down. So I would draw a straight line going down and label that motorcycle. The horizontal direction is positive to the right. Motorcycle is going to the right. So we're going to have a positive x velocity. And then again, that velocity is constant. So we would just draw a flat line. So label that motorcycle. Then part 2 says we now repeat this with a car that's going twice as fast. So the velocity is 2 v naught. So over here on this graph, my velocity is going to go from this value to a value twice as high. So there's my car's initial velocity, but it's still going to be constant after it leaves the roof. So I would just draw a flat line at a higher value, twice as high. I mean, it's just a sketch, but twice as high as the motorcycle. The vertical velocity, though, is going to do the exact same thing. It starts off with a vertical velocity of 0. The acceleration is still g, so the line would have the same slope. And so the car and the motorcycle would have the exact same graphs in the vertical direction. Okay, I hope you found this warm-up helpful. Now it's time for you to go do some on your own. Do be sure to check your answers as you're working, and be sure to be careful about rounding off these numbers. Your assessment on this, remember, is going to be in the lab, so accuracy is going to be important. So just kind of keep that in mind as you're working through these. Till next time, ta-ta.